Well, it is my great pleasure to have here Professor Han Luye, which took the Nobel Prize last year for the wonderful work that she have done on very, very, very fast laser. And you have, indeed, she is speaking of attosecond laser. Now, lasers are extremely important technology, not only for application, but also for doing fundamental research. And the attosecond lasers is something that is extremely useful because one can pin down the properties of electron movement, something that already 20 years ago would seem to be science fiction. Of course, the history of very fast laser is something that has been very, very long. There have been wonderful experiments that were done also in Italy by Svelto, Bellini, and so on. But the real crowning of this research has been the result of Attosecond, which opened a new avenue to research and also to application. Now, before starting the conference of our Nobel Prize, she is also a fellow of the Accademia dei Lincei, but for different reasons, essentially connected to the pandemic, we never gave her the pin of the Accademia. So I would like to present her the pin. Maybe you can hear, so someone is going to make congratulations. And so thank you so much for having accepted to be a member. And before, okay, you may help. Yes, it was a problem with COVID. And before you start, I would please to have the Swedish ambassador, who was very kind to come here, to say a few words. Thank you so much for coming.
Thank you, Professor Parisi. Thank you, Nobel laureates, ladies and gentlemen. Thank you very much for inviting me here today. Sono ambasciatore di Svezia, ma prima sono stato ministro del governo di Svezia dell'università e della ricerca. When I come in, this is a really European event because Italians, Swedish, French. Now, okay, the French ambassador believe that Anne Hullier is a French professor, but we believe that she is a Swedish professor. Of course, the fact is that she is both, of course. The origin is French, from the country of Marie Curie, but she is today, since 30 years, professor at the University of Lund in southern part of Sweden, and with a Swedish family and so on. So I'm really honored to be here and listening to this seminar today. This palace has also a Swedish-Italian history, as several of you know, because Queen Christina of Sweden resigned in the 17th century, 28 years old. Sweden had then left the Catholic Church 100 years earlier, and she moved to Rome to become a Catholic. That was a very big step because there was a big political fight in Sweden becoming Protestant, and there was the 30-year-long war where Sweden was on the Protestantic side. Her father, the king, was killed in the battle with the Catholics, but she converted to Catholicism. She was seen as a traitor for several hundred years in Sweden. Here she was a hero, of course, and the Pope gave her this palace to live in. She lived in this palace for 30 years. She died here, and she is today buried in the crypt together close to St. Peter himself in the Basilica San Pietro. So it's, today we have forgiven her in Sweden, I can say. Today, she's accepted today. So, but this palace has a very big Swedish-Italian history, and that is also, I always feel humble for this. And one more thing. You know this Accademia di Lincei, and you know more about it than I do, but it was founded in the early 1600s. But it had a really, really dip when after the conflict between Galileo Galilei and the Catholic Church. When Queen Christina moved into this palace, she opened this palace up for free research again and gave life to Accademia dei Lincei. So she was also fighting for free research. So that's also why we have forgiven her. So thank you for inviting me, Professor Parisi, and thank you, and I look forward to listen to Professor Ullier. Thank you.
Thank you so much. So welcome to everybody, to those that are here and to those which are hearing us by streaming. And now we can start with a wonderful conference of Anna Louvière. Okay, you have the floor.
Is this working? Yes? Okay. Yeah? Not really? Oh, it's a real pleasure to be here, and I learn a lot of history at this moment, so it's really interesting. So I'm going to tell you about why I got this Nobel Prize and this physics of attosecond science. So I will try to speak to, at the same time, to physicists and non-physicists, which is very difficult. But so if sometimes you are lost, just wait. Maybe the next slide you will be back. So I have, at least I have tried. So this is just an introduction about time. This is an arrow of time. Starting from the age of the universe, which is 13.8 billion years, 10 to 18 seconds. And now we can go down here to, now I'm going to use this laser. Giorgio, would you like to move? I'm afraid to hit you with this laser.
No, please go on.
Okay. Okay, I'll do my best, but yeah, okay. So, and we are going down to 1 attosecond here, which is the time scale I'm going to discuss. So here you have some astronomical times with the year, the day. This is the age of humanity. This is the heartbeat. It's 1 second. Millisecond, it's the mechanical time. Then you have electronic time, it's nanosecond. Time for vibrational motion in molecules is of the order of femtosecond or a few femtoseconds. And then time for electron to move in atoms and molecules is of the order of attosecond, a few tenths of attosecond. So the outline of this talk is a little bit historical. I'm going to tell you how the ideas and the main results came about since actually the invention of the laser. So there will be 4 different parts telling you how this field has evolved. So nothing would have happened without the invention of the laser in 1960 by Theodor Meinmann. This is a picture of one of the first laser, ruby laser, and the Nobel Prize for invention of the laser went to actually the background to Charles Townes, Bazov, and Prokhorov. We are going to use 2 properties of laser light in our research. The fact that you can confine light during very short pulses, and then the fact that it's intense radiation. The laser led to new field of research almost immediately. One of them is called nonlinear optics, started with an experiment by Peter Franken in 1961. And this is a field where you can generate new frequencies by a strong interaction. And here you have absorption of 2 laser photons and emission of a photon at frequency 2 omega. This is second harmonic generation. This is the setup that was used by Peter Franken. Very simple. You have a laser. You focus this laser into a material, here a piece of quartz, and then you analyze the radiation with a prism, and then you have a detector. Nobel Prize to actually to laser spectroscopy went to Nicolas Bloembergen and Art Shallow, and Nicolas Bloembergen is considered as the father of nonlinear optics. And the same year, you have also a Nobel Prize to a Swedish physicist, Kai Sidberg, who invented high-resolution electron spectroscopy. And we are going to use electron spectroscopy a lot in our research, as you will see. The second field that was open, thanks to the invention of the laser, is atoms in strong laser fields, multiphoton processes that were predicted theoretically already in 1931 by Maria Goeppert-Mayer, who was the second woman to get a Nobel Prize in physics. So here you have a 2-photon process where an atom is excited by absorbing 2 photons. And you can also have multiphoton ionization, where an atom is ionized by absorbing many photons. This was pioneered by actually Russian scientists in the end of the 60s. In 1979, Pierre Agostini and co-workers in Saclay, France, discovered the phenomenon of above-threshold ionization, where an atom can absorb actually more photon than needed for the ionization. And you can detect this by measuring the electrons that are emitted and the energy of the electrons. My thesis work, beginning of the 80s, was about multiple ionization of atoms using multiphoton absorption. At that time, we had the idea that in this interaction between atoms and laser, we create excited atoms and ions that could decay by emitting fluorescence light. So we set up an experiment to observe this fluorescent light. And so this is the principle of the experiment. It was performed at the Commissariat Énergie Atomique in France. At that time, I was a young researcher. I had gotten permanent position, but I was very young. And so it looks very much like the experiment by Peter Franken, except that now we have a gas of atoms, and here we use a grating, but same function to analyze the radiation. And this is how the laser looked like, and this is how the experiment looked like. It looked a little bit old. So this was a picosecond laser, and this is the experiment. It's a vacuum chamber, this size. The laser is coming here, is focused, and then we have a grating to analyze the radiation and a detector. We did not see fluorescence. We saw something else, which was very exciting. And what we saw is the generation of high-order harmonics of the laser field. And this is one of the first spectra obtained in argon gas. Here you see many harmonics of the laser field. So this means that it's a multiple of the laser frequency. For example, here 25 times the laser frequency. If we plot the distribution of these harmonics as a function of order, you have this very unexpected behavior with this plateau distribution for many, many orders, which means that all the harmonics have approximately the same intensity. And this was very exciting at this time because we were thinking in terms of perturbation theory, writing the polarization in the medium as a sum of exponents of the electric field of the laser. And for this to be valid, you need the first term here to be much larger than the third, much larger than the fifth, etc. And the fact that we saw this plateau means that this is not the case. It's non-perturbative. You can see that we only have odd orders, and this is due to a symmetry of the interaction. It's the medium has an inversion symmetry, and this kills the even orders. So if you go now from, we start with the laser frequency, which is in the infrared. Here somewhere, this is an electromagnetic spectrum. You have the visible part here. This is X-rays. So we start here somewhere in the infrared, and we multiply by an integer, for example, 33. We end up in the region of the spectrum, which is called extreme ultraviolet. Not really X-rays, but harder photons than ultraviolet. So this region with wavelengths of the order of 10 nanometer. Now, just to make an analogy for those here who are not physicists, I'm sure you have heard about harmonics before in your life, if you play or listen to music, and it's very similar. This is actually the spectrum of alto violin. If you play the A string, you get this spectrum. So you have the tone, but also many harmonics. And actually, the number of harmonics in a music instrument is what is making the klang of a music instrument. And string instruments have many harmonics. And you can compare with what we get. So, of course, here we talk about harmonics of light. For music, it's harmonics of sound. But in both cases, you have a strong interaction between, in this case, atoms. Here is the strings of the instrument. And due to the laser, this is due to the interaction with the bow of a violin. So it's same. There is, I think, a strong analogy. To understand these processes, I mean, what I find very interesting with this phenomena is at the border of two fields. One is atomic physics, quantum mechanics. You need to understand the response of an atom to strong laser radiation. This is described by Schrödinger equation, which you see here. You have the interaction here. You have the atomic potential and the laser atom interaction. We can describe the electromagnetic field classically. And here we use the dipole approximation to describe this interaction. The difficulty is that both terms are comparable. So this is, again, a strong laser atom interaction. You also need to consider the response of a macroscopic medium to the interaction. And to get efficient harmonic generation, you need that all of the waves emitted by all the atoms be emitted in the same direction and at the same time in phase with each other. This is called phase matching. So this problem is described by Maxwell equations of electromagnetism, which can be simplified to wave equations such as the one that is written here, where you have a generated field here, and due to a source, which is because of the polarization of the medium. So to describe completely this process, you need to solve both equations. And this is actually the first attempt to understand this phenomena was to simulate and with actually good agreement between experiment and theory. It doesn't mean that we understand better the physics, but this was the first trial to understand this phenomena. Continuing on the music analogy, you can think of that your medium of atom is a gigantic orchestra with billions of musicians, not only 10 atoms in the medium, but billions. And we need all of these musicians to play music together in order to get something out. What about attosecond pulses? And the idea for attosecond pulses arose almost at the same time. It was a natural idea for people dealing with lasers, because it's the same idea that you have with mode-locked laser. So here's the idea. I'm plotting here 3 harmonics, 17, 19, 21. Let's assume that these harmonics are phase-locked, which means in phase with the same phase, which means the maxima are at the same time, at some time, like here. And because of the periodicity of the process, a little bit later, which is half a laser cycle, the minima will be together. And then again, the maxima, the minima, etc. So let's assume that this is the case. And now let's sum these 3 different waves. You can do that with your head. What you get is that at these times, you have constructive interference of all of these waves. They add together. Whereas in the middle here, they have slightly different frequencies. So you add plus or minus. You have destructive interference. You get almost nothing. And then again, you have a small pulse of light, etc. So you create a sequence of short light pulses. We can plot the intensities. This is the electric field, but if I represent the intensity of light, you see this is called train of attosecond pulse. If you sum not only 3 harmonics, but 10 harmonics, and if they are phase-locked, you can obtain very short pulse. And this is a simple expression of Heisenberg principle. If you have a large bandwidth, many frequencies, and if they are synchronized, then in the time domain you have very short light pulses. So is undetermined in frequency and very determined in time. So this was a very exciting idea. So the question was, are these harmonics phase-locked or not? So now we come to part 2, and we are in the 90s. I call this progress in technology and understanding. And maybe one of the first things that happened at the end of the 80s, beginning of the 90s, huge progress in laser technology with the invention of the chirp pulse amplification made by Gérard Moreau and Donna Strickland, leading to a Nobel Prize a few years ago. You have also a new laser material called titanium sapphire, a new technique to generate short pulses called Kerr-Lenz mode locking. And here you have a Swedish scientist in Lund that decided to invest in this new technology and to actually ask a laser company to put together these inventions and build a prototype, a terawatt laser based on titanium sapphire at the Lund Laser Center. And I think this was really a good decision because this led to, this laser was going to be the base for this field of research during 20 years. Now it's starting to change again, but at that time it was really a very good technology for this field of research. This was also a good decision for my own life. I will come to that afterwards. In parallel, we in France, we build dedicated instrumentation to study this phenomena, and much more modern equipment. And you have a picture, this is myself a long time ago, and my first two students in France, Philippe Balcou and Pascal Salière. And so we build these instruments, which you have here. It's about the same as I showed you at the beginning. You need a gas, you have a lens, a lens, a gas, and some optics to analyze the radiation, and then a detector. I put a computer here because this is really the time where personal computers came into the laboratories, and they look like this. And it was really a revolution in how to take experimental data. We could start writing small programs to analyze the data. We could see the result light. So it really changed how we did measurements. And this is also a little bit, at least for me, the beginning of European collaborations. And the European Union proposed some instrument for European people to work together. And so as a young researcher, it was very interesting. We started talking to each other. And so we got invited by the scientists in Lund to try their brand new laser, to bring this instrument that you see here in the truck and to do experiments. And in this, this is where I met my future husband, and this is the reason why I moved to Lund 2 years after the experiments that we did together. That was in 92. And this is some result from this experiment. Here you see a beautiful harmonic spectrum obtained in helium gas, now going to the 93rd harmonic. So you are in wavelengths of almost 8 nanometer. And this is a result where we study, and this is really thanks to these computers that we could use, as well as the repetition rate of the laser, which was 10 hertz, 10 shots per second, much better than before. And now we could study the intensity of the harmonics. You have this harmonics here as a function of the laser intensity and as a function of different parameters. And thanks to this study, we could understand much better the process. 93, huge progress in theoretical understanding. The Nobel Prize is awarded to the experimental method, but I would like to say that in this field we have been working hand in hand between experiment and theory all the time, and this has been really important. And here is progress in the theoretical understanding by Ken Kullander, Ken Schaefer, Paul Corkum at the same time, and also Maciek Levenstein, who proposed the quantum formulation of this three-step model, which is called strong field approximation. So here you have an illustration of this three-step model, where what you see here is an atomic potential, which is distorted by the laser in one direction, and you get at some time a potential barrier here that an electron in the ground state here can go through. This is tunnel ionization. Then the electron is free. It's driven by the laser field, which is a strong force. But the laser field change of sign, the electron is going to come back, and then there is a certain probability for recombination back to the ground state. This is a coherent process, so it's an interference effect. And this recombination is accompanied by the emission of XUV photons. And if you consider the different possible trajectory, you find that this emission corresponds to a light pulse which is in a few hundred of attosecond duration and a bandwidth of a few tenths or a few electron volt. And now if you, suddenly we have a very intuitive picture of the phenomena, and now if this process is repeated twice per laser cycle on this side, and then the next half cycle on the other side, and then again and again, and if you go into the frequency domain, you recover the spectrum of high-order harmonics. We continue to do progress, and here is, I think, one of a very important experiment that we did at the end of the 90s in Lund, together with, so on this picture you have Mette Gårde. She was my first PhD student in Sweden. She's coming from Denmark. Now she's professor in Louisiana State University. You have Ted Hensch, Marco Bellina, who is here. So this was a European collaboration, and this is myself. And what we did was to simply to look at the coherence of these high-order harmonics. Is this coherence radiation? And to do that, we create two replicas of the harmonic source, of course from the same laser. And then we look in the far field. So here in the middle you have a grating to select one harmonic. But we look in the far field where the light emitted from this two sources interfere with each other. And this is the result for the 15th harmonic, and you see beautiful interference fringes. In addition, you see two regions of two contributions from these harmonics. You have a collimated part and more divergent part. And this was the first time where we could see a little bit in real life these different electron trajectories that I mentioned. And if you consider the important trajectory, you see that you have short trajectories leading to this collimated radiation and long trajectories leading to this divergent emission. So this was the first time where we could see experimentally this electron trajectory. There is also more progress in laser technology. Now I'm at the end of the 90s. And the important development was very, very short laser pulse. And this was going to be very important to create isolated attosecond pulse. And you have the development by the group in Milan with Professor Orazio Svelto here, with the important technique of the hollow fiber compression, where you can get very, very short laser pulses. And also it was realized that it was important to measure and control what is called the carrier envelope phase, which is the difference between the envelope of a pulse and the amplitudes of the electric field. So it was important to control this difference. So now I'm coming to the measurement of attosecond pulses. And again, there are two measurements approximately at the same time, performed by Pierre Agostini and Ferencross. Ferencross, using these new techniques with very, very short laser pulse, could create isolated pulse. And Pierre Agostini measured attosecond pulses in a train of pulse. I'm not going to give you many details on the technique. This is a generalized slide about the method that was used. It's cross-correlation methods. So what you do is you start from a laser, you generate attosecond pulse in a strong laser field, as I told you before. Then you send these pulses together with a probe laser into a second chamber where you ionize and you detect the electrons. And these are the first results obtained by Pierre Agostini for a train, 250 attosecond pulse. First result obtained at the Technical University in Vienna, single attosecond pulse, and it was more results. They moved to Garching, and they got shorter pulses a few years later. And this is really why they got the Nobel Prize. Then you have very nice results from the group in Milan, getting very short pulses, 130 attoseconds in 2006. And this is a more recent result showing you where the record, what is the record at the moment, is 43 attoseconds. You can notice that this is very, very European research. This research is, has been driven in Europe. I think it's very much because of this idea that we should collaborate with each other, and we have European instruments to help us to do that, the networks, and also the access to laser infrastructure, Laser Lab Europe. They have really helped fostering attosecond science in Europe. And I think this is still the case, that Europe is still very, very strong in this field of research. Now China is really investing a lot in this field, so we will see how it develops. But I have a little European flag here because I think it's very much because of the European Union that we have collaborated with each other and have this communication and exchange of ideas and results between us. So a little detail on this measurement now, and I will start by the experiment of Pier Agostini. He used an interferometric technique to measure the phases of the harmonics, to really see whether these harmonics are synchronized. And this technique is called RABBIT, which means reconstruction of attosecond beating by interference of two-photon transition. And he used two-photon ionization, as you see here, leading to electrons at a different kinetic energy. And you can reach these sidebands by two different paths. This path here, and then the path using the next harmonic, and then emission of radiation. Now this is quantum mechanics. You add amplitudes, so you have amplitudes for this process and this process. And this sum depends on the relative phase, so it depends on the phase of the harmonics. And then you have a delay with the laser field, so you have this phase. And now the signal that you get when you measure these sidebands oscillate at a frequency which is equal to 2 omega. This is this phase minus omega tau, so 2 omega tau. And then you have these phases. So doing this measurement, Pier Agostini could measure duration of attosecond pulses of the order of 250 attoseconds. This is the results obtained by Ferencz. He used a similar technique, which is called a streaking technique. This is the first result, which I'm not going to describe. It's leading to 650 attoseconds. This is a later result, which is much nicer and maybe easier to understand. And the result is really in this trace that is going up and down. And the idea here is that you create an attosecond pulse. This attosecond pulse ionize a gas in the presence of an electric field, a laser electric field, and depending on the time of ionization, the electron can get momentum from the laser field, and it can lead to increase of energy or decrease of energy, as you can see here on this trace. And from the shape of this trace, you can recover the duration of the attosecond pulse. Now I'm coming to the part 4, which is opening to other research field and application. And first of all, I mean, this is how I started this talk. Can we use this very short light pulse to follow the motion of electrons in matter? This is just a picture of a Bohr's atom with particles rotating around the nucleus. If you just calculate the time for an electron on the 1s shell in this Bohr's atom, you find 150 attoseconds, which means that this is the right time scale. But of course, you don't have this. This is quantum mechanics. This is more like a wave around the nucleus, and this is nothing we can measure. However, we can measure other processes, like, for example, photoionization, where you have emission of an electron due to absorption of photon in the XUV range. This is the photoelectric effect, which was explained by Albert Einstein in 1905. So when you see such a picture, I'm sure you think about this particle, which is emitted as a particle, going to a detector, and you click, you measure the energy or the momentum of this particle. Now, with our technique, we are going to measure really the wave property of this particle, the phase. This is a wave, and it has a certain phase, and this is what we are going to measure using the same technique as was done by Pierre Agostini in his measurement, using an interferometric technique. And I'm not going to give you detail, I'm just showing here a measurement. This is photoionization of neon atom in the 2s shell and in the 2p shell, and the information is obtained by looking at the phase of this oscillation that you see here. And this is what is giving us the temporal information. Just to make an analogy with music again, you have a metronome here. So a metronome is giving the time when you play music, and it's a wave motion. The mechanical tip of the metronome is really making a wave motion, and this is, I think, very similar. So in this measurement, you can also think of a clock. What is the duration of 1 hour in our clock? It's 1,300 attoseconds. This is half the laser cycle. This is 1 hour in a clock. And what we can do is we can measure a difference in 2 arrows on the clock. We cannot measure the absolute position of these 2 arrows. This we don't know. Absolute time is too difficult, but we can measure a time difference. And this is what we can do accurately. We can measure here the difference between 2s ionization and 2p ionization. And this is the result showing this difference, this delay. And you see that we have a precision which is of the order of about 20 attoseconds. This is as a function of photon energy. Let me show you another result, which is more interesting from an atomic physics point of view. And this is ionization in the 4D shell of xenon atoms. We also measured these time delays for ionization in the 4D shell. And here you see positive time delays, which are due to a giant dipole resonance in the photoionization of xenon. And then you have a long delay here, which are due to spin-orbit interaction. So this is what we started to do since a few years. I think the real challenge of attosecond science will be to use this technique that we are benchmarking in atoms, in molecules and condensed matter. This is really, I think, the goal of attosecond science, but there's still a lot of fundamental research to perform to really use this radiation in more complex systems. An unexpected application, which is coming at the moment. This has nothing to do with what I was telling you. This is a picture of Moore's law, where you have actually, at the beginning, I think this was the size of the transistor as a function of year, and but now this is the count, the number of transistors that you can put on a chip as a function of year, and the idea is that this curve should continue. Now we are at the range of I think the future now is about 10 nanometer, and also they're starting to pack up transistors on 3 dimensions in order to actually continue this law. Now to do that, you need 2 techniques. You need lithography to make the chip, to print out this processor on the wafer, but you also need metrology to control what you are doing, to see if there are defects and to control them. Now the present where we are now is using actually EUV radiation or XUV radiation at 30.5 nanometer. And this is using plasma-based radiation. But the semiconductor industry is really looking for a source to do this metrology of the wafers, which are printed using this radiation. And this is where this high harmonics, so here we're not using really the temporal structure of the harmonics, but the fact that this is coherent light with many, many frequencies. So this is an application which is investigated by this big company, ASML in Holland, and actually they are building prototypes using high order harmonics. And this is the idea, is to use this source to focus that on a silicon wafer with lots of processors on, and then to look by diffraction techniques using multicolors and to really image, and especially in the 3 dimension, this integrated circuits. So what is the next step in attosecond science? Well, I think this field is really opening in many directions. The field is becoming actually very large, with application in atomic spectroscopy, that I showed you, maybe attosecond chemistry, condensed matter physics, industrial application, also a little bit towards quantum information, quantum dynamics. Since 2 or 3 years, we have also a new way to generate attosecond pulses using free electron lasers. And these pulses are quite different from the one that we generate via harmonic generation. They are in the X-ray range and much higher energy per pulse, and also a single pulse. So I'm now coming to the end of this talk. I would like to thank my research group. This research is done by teams of people, not thousands of people, but maybe here we are about 20 different projects, and this is the organization funding this research. And I would like to thank very much the Accademia de Lincei for this coming here, and also since I became a fellow of the Accademia 2021, so it was 2 years before the Nobel Prize. And also big thanks to Orazio Suelto for accompanying me during these 2 days. Thank you very much.
Wonderful physics and a mixture of past, present, and future.
Yeah.
So thank you so much. And I ask if people have some question, comment, statement. Yes, please. Microphone, scusi. One moment. Sorry.
Thank you for your beautiful talk. The question is, you used gas in order to generate a high harmonic generator, so higher frequencies. What happens if you use, instead of gas, condensed matter, so solids?
Yeah, I mean, this is a new area in our field, is to use thin films to generate harmonics. It's appeared a few years ago, and now this is used a lot to, especially to characterize your solid by looking at the harmonic light. So for the moment, it's mostly it's not very hard X-rays or photons that are generated. So it's mostly used using a long wavelength to start with and getting harmonics in the visible. But there is a lot of research around this. Again, the main idea for the moment is to characterize the solids using the harmonics. It's not so much to use the harmonics yet, but maybe it will come.
Thank you very much.
Just a simple question by a simple chemist. As a physical chemist, in the list of the people who got Nobel Prizes, we have a friend who passed away, Segui,
Yes.
who was awarded the prize for what we call femtochemistry. So there are, of course, 3 orders of magnitude in time, and in those times, we were thinking just sort of being at the edge of the progress in physical chemistry because of limitation to the uncertainty principle. In other words, the debate was, can we go at shorter pulses, then we will be involved in larger spread in energy, so that the resolution in photochemical, photophysical experiments would have been limited, and apparently that was not true. And the talk had been showing. Can you quickly give a hint of how to win over the uncertainty principle?
Yes, this is a very good question. I like it very much. Can I get back the slides? I'm going just back a little bit. Yeah, I can back. I mean, this results, for example. This is the beauty of the Attosecond pulse train, because we use end of the high harmonics, because with this interferometric technique using Attosecond pulse train, so think about these are harmonics, the spectral resolution is given by the harmonic widths. It's not given by the Attosecond bandwidth, is given by the harmonic bandwidth. So we keep a high spectral resolution. And the high temporal resolution is given by the interferometer. So it is 20 attosecond. So this is our way to, not to break Heisenberg principle, but to circumvent it, using the fact that we repeat the measurements many, many times every half laser cycle. So, and I think this kind of thing, of course, what we call the spectral congestion in molecular physics is a major problem. But I think we have ideas to, we are working on improving this, and I think to keep high spectral resolution and the high temporal resolution is, we try to keep both using this interferometric type of technique.
What would be the name of 10 to the minus 21?
It's called Attosecond. Attosecond. zeptosecond. Yeah.
21.
Yeah, but this is more in the future. But I think there are much more. There's a lot to do at this level.
Massimo?
I would like to thank Anne also for the highly tutorial level in these lectures, really teaching about an adventure. Having here the presence of the ambassador, I would like to comment on the fact that this Nobel Prize and this lecture is also the demonstration of the importance of Europe.
Yeah.
I very much appreciated Anne when she said now of Europe, which wanted to organize science following infrastructures. So when Anne came to Florence, when she mentioned the experiment of Marco Bellini, this was because from one European infrastructure she was coming to another really born European infrastructure. And then of course, as researchers, we are proud that the scientific world, Europe is there. And then the years that Anne was so reminding are also the years where a wall was broken between ultra-fast lasers, pulsed lasers, and continuous wave lasers. The world was divided into two. I mean, physicists, precise measurements were all done with ultra-stable laser. Virgo is an example, and instead the pulsed laser was a matter of chemists and so on. Now this experiment created a sort of breaking the wall. This was an example. The other one in the picture that she showed, there is also Ted Dench, who also got the prize because he used the pulsed lasers to make frequency measurements. So really, I think that this Nobel, personally, I think that this Nobel Prize is also the triumph of our research in tabletop research in Europe. These are infrastructures are tabletop infrastructures. We don't need, and then and Italy is present on this thanks also to the complementary interaction between Florence and Milano, who also is our companion in this adventure. So really thank you, Anne, and thank you for the organization of this meeting.
Thank you.
Well, the ambassador want to say something, and after maybe Orazio, and after give.
No,
It's okay. It's okay.
thank you very much, Anne, and thank you for this meeting. Maybe I'm maybe the only in the room who are not a scientist or a scientific student or something. So, but I really appreciate it anyhow. Since we have two Nobel laureates in the room, I have to I have to tell us, because when I was minister in Sweden, I went to China to a meeting in Beijing with the Minister of Research there. And he told me directly, you have to give more Nobel Prizes to China, he told me. Okay, you see, the government is not involved in this. It's a scientific prize, it's the scientists. Yeah, I understand. But you have to give more Nobel Prize to China. This, of course, reflects the difference in societies, of course. But speaking of that, the politics is important to create the foundations for the research, like the European cooperation, as you said. Also, to fund basic research. Now, this is basic research.
This is very much basic research, and it's basic research that taken time.
Yeah.
I mean, the first high harmonics, this was in 87. It's 37 years ago.
Yeah, you started with Einstein there and so on, so it's a very long time. So,
Yeah.
but that's a problem when it comes to politics, and I suppose that it's maybe not in Italy, but in Sweden and in all countries. It's very popular to speak about applied research and innovations.
Yeah.
Basic research is much more. Most of the people don't understand what it is about, and that's why it's so important to invest in because without basic research, there will no innovation. Applied research is, of course, applications of the basic research. So, but having said that, now I'm going to contradict it with, because this is basic research, but if you speculate a little bit in the future, in what areas, and it's only speculations, and I respect if it's not possible to say, but in what areas in our modern society could this be useful, if you just try to speculate a little bit?
Yeah, I give you two answers. I think that what I mentioned at the end with this application in semiconductor industry, this is a great application. It's not really used yet for future generation. I think it will be used. So, but they are building prototypes, so we'll see where it leads. So, but this is really exciting, and it will be. You will have, if it works, then you will have a consequence on your future smartphone or computers. This will be huge. Yeah. I'm looking at you. Yes. So that's one answer. And this was completely unexpected. This arose a few years ago. We were contacted by this big company and said, can we use your radiation? And so we started talking to each other. Completely unexpected. Then my second answer is, this is more in the future, but I hope that this will be useful in chemistry, actually, in condensed matter, to really understand better the nature, and maybe if we can look at, so this will be to look at, thinking of chemistry, the beginning of chemical reaction induced by an electronic transition. So at the beginning, very often you have an electronic transition, which means motion of an electron. If we can look at this electron dynamics, and if we can look at, which means also that we can maybe affect and control, that would be huge. But there are many, many years of basic research which need to be done in order to really lead to application. That's what I think.
All right.
Yeah. Well, first of all, let me congratulate Anne for your beautiful, I heard you at Politecnico, and then you changed drastically for making a much more beautiful here talk. Now, I want to make two comments. One related to what the ambassador said before about basic science and applied science. I personally not to use these two terms, but rather innovative science. What is really important is innovation, which can be not only in basic but also in applied science. And one of the classical examples of this is the laser. Being one of the early starters in this field, in the first 10-15 years, nobody knew what the laser could be helpful for. As a matter of fact, for the first 10-15 years, people were calling a laser a bright solution looking for a problem, because nobody knew what application was there. But now, you see, lasers is everywhere. Now, the second, more specific comment is that at the beginning, the leadership in the laser field was both from the United States and Russia. As a matter of fact, the Nobel Prize was given to Charles Towns from the United States and Basov and Prokhorov from Russia. Europe was outside. Then when ultra-short pulses started, at that time it was picosecond, Europe began to enter into the play. And now, with attosecond science, you may have noticed that the three people are all from Europe, the three Nobel laureates. So I would say now that the leadership in this field is in Europe, thanks to this collaboration that Anna was telling about.
Yes.
I have an idea about application, the opportunity to integrate your methods with the biological system offers an innovative and powerful perspective to decipher and reconstruction the molecular history of disease. In particular, the combination of complex system approach with molecular dynamics analysis could reveal the underlying molecular mechanism of disease, allowing to trace the causality of events in cells over time. Is it possible?
I don't know. That's a little bit the hope, but again, I think we have many years in front of us to really show that this is possible, and many years where there should be really work together between physicists and chemists and biologists.
Yes, my question, I am a PhD candidate about medical genetics.
Yeah.
And I think that your results, Lulier and Parisi, are a very big opportunity for medical science.
Yeah. I can mention just a little disclaimer or something like that. Ferencross is talking about medicine application in his Nobel lecture. And the reason is that he's now going into a direction, and it is not really using attosecond pulses as I have discussed, is using the control that he has on the electric field of the laser. So really very, very precise control, which is on the attosecond time scale, but the lasers are in the infrared, mid-infrared even. And so he's using this control to, then he's sending this laser pulse into blood samples and try to detect signs of disease on how the electric field is changing when it's going through blood sample. So this is, I think, what he's talking about. To me, it's a bit different. It's not really a consequence of what I've been discussing. It's a different way, but I think it's very interesting. But I just want to mention this for clarity. Yeah.
Thank you.
Okay. If there are not other questions, yes, please.
One here.
Sorry.
Very fast question. I also congratulate. Thank you very much for the lecture. My question is the following. You have focused that it's key to phase align higher order frequency pulses in order to obtain attoseconds. I assume that there will be some phase locking mechanism. Is that the barrier to achieve, or the obstacle or the critical aspect to achieve the very short pulse, or phase alignment is somehow not an issue?
It is very much an issue, and actually in reality the harmonics are not exactly phase locked. There is a chirp which is called the attosecond chirp. So this electron, they do not come back really at the same time, depending on the energy. So there is and this is absolutely limiting the duration of the pulse that you can get. If you, we can get now many harmonics. You can go to the kilo electron volt range. So huge bandwidths. So in reality, you could go to really a single attosecond if you would just do forget about this phase difference. But this lack of synchronization is limiting the pulse duration that you can get. Yeah.
Un'altra
Oui.
domanda e poi chiudiamo.
Oui.
Another question.
Merci, Madame, pour la belle conférence, Madame Lullier. I follow in English. My name is Paola Antolini. I am United Nations University for Peace, Science for Peace. And I had the chance already to organize with Donna Strickland and Gérard Mourou in Paris to encourage girls and women to choose the scientific discipline. You belong to this minority of ladies following Marie Curie that got the Nobel Prize. So, yes, thank also to Professor Giorgio Parisi for co-organizing this beautiful and illuminating, inspiring activity. Now, it seems to me that you quote the word beauty while you were talking about the beauty of the discovery of science. So do you share the assessment of Marie Curie that we believe that science is a beauty as well, that science can be poetry? And how do you feel in this small minority but growing minority of women that got the Nobel laureate for physics is especially limited? Thank you. And we know that it happened in Stockholm in 1903 because Pierre Curie insisted to share his Nobel nomination with Marie. I work as well with the granddaughter of Marie Curie. So your point of view, science and society, and beauty and poetry in science will be wonderful. Thank you.
This is a very nice comment. I didn't know about that she said that, so I would like to have the quote. Yes, I agree. I think there is something I've gotten many interviews since I got the Nobel Prize, and so what I often say is that I'm not talking about beauty so much, but something called intuition. And to me, intuition is there's, I don't know if it's me or.
Yes. Okay.
So I think intuition is very much an artistic thing. You follow some kind of intuition in science. So, and absolutely it's beautiful. Nature is beautiful. The physics of these harmonics is beautiful. So I think this is very, very, very much true. Regarding women in science, I am of course very proud. Maybe it's better to continue without microphone. This is the, okay, is this working? Yeah. So I'm very proud to be the 5th woman to get the Nobel Prize in Physics. I hope this is changing now. There are 3 women the last 5 years. So I think there is a change of trend now. And hopefully there will be more and more women in physics and also women getting Nobel Prize.
Okay, so I thank you again for this wonderful lecture, wonderful answer to the questions, for taking so much time. So thank you again.
Thank you.